Hi, this is Dane Quinn from the University of Akron, and today I'd like to give a video lecture that really focuses on the response of a single degree of freedom system to harmonic excitation. So in a previous lecture, we actually went through this and we derived the solution. In today's lecture, I'd like to spend some more time and really investigate how that solution varies as the different parameters of the system change. Here's what we started off with. We have a simple spring mass damper system, right? Spring stiffness K, damper, damping coefficient B, and we apply a force, F of t, that's time dependent. And we further assume that that force is harmonic, sinusoidal actually, with amplitude F naught and frequency omega. In one of our earlier lectures, we went through and we showed how this general excitation can be the basis for really looking at lots of different kinds of forcing, cosine forcing in particular, right? But more generally, any kind of periodic forcing can be written in terms of the response of this system. So as we vary the forcing amplitude and frequency, it's really important that we understand how the spring mass damper system responds. Again, in this previous lecture, we went through and we showed that the response is harmonic as well, with a different amplitude given by x and this relationship, also with a phase shift, phi, relative to the forcing of the system. So if this light blue line represents the forcing, and here I've basically described as F over K, right? So this has units of displacement. Then the response lags that forcing, right? So it's shifted in phase and at a different amplitude, but it still responds with exactly the same frequency as which it was forced, right? So again, the forcing is amplitude F naught, frequency omega, and the response is amplitude x and the same frequency, omega, with the addition of this phase shift. So again, we went through and we derived this solution previously. But what I really want to do is understand how the amplitude and phase vary as we change these system parameters. If this was only about just, here's the system, right, here's some numbers, find the amplitude, then I'd be done, right? I could just use this directly. But I want to do something deeper, something more. I want to really look at this in terms of what we would need for design, right? So how do I choose the stiffness, say, to get a desired response, right? How does this system respond as maybe the mass changes, right? You could think about, again, a design problem. Do I make this light? Do I make it heavy, right? What's the overall response of the system? So that's really what I want to focus on today. Now, in order to do that, we'll actually take the amplitude and phase that we have here and we'll simplify these, right? So we'll do this in a couple of different ways. The first thing we'll do is actually we'll factor out the mass, right? So we'll have F naught over m, and then what's left is 1 divided by, okay, so we got the square root. When I factor out m from here, we end up with k over m minus omega squared plus b omega divided by m, again, quantity squared. Now, if you notice, we see some familiar quantities. This k over m, for example, is the natural frequency. And b over m, right, we've actually seen that before as well. So if I go and I describe this relationship in terms of the natural frequency and damping ratio, we end up with the following. Right, again, we have F naught over m that we've factored out, and then 1 divided by square root. Okay, so k over m is the natural frequency squared, so that's omega n squared, and then minus omega squared. B over m was actually 2 zeta omega n times, again, this omega squared. So by factoring out the mass, we can write this kind of complicated piece in terms of the natural frequency and damping ratio and the forcing frequency. So now I'd like to do a similar thing by factoring out the stiffness. So again, we have F naught over K. Right? When I do that, well, we're factoring out K. So this becomes 1 minus m omega squared divided by K, quantity squared, plus then b omega over K squared. All these things are exactly the same. I'm just representing them in different forms because eventually I want to highlight, for example, what happens when we change the natural frequency or what happens when we change the damping ratio. So once again, simplifying this, we have F naught over K, and then what's left here becomes 1 minus, well, K over M was again omega n squared. Right? So I get actually omega squared divided by omega n squared plus, well, when I simplify this, we end up with 2 zeta omega divided by omega n. And you might want to pause the video now and work through some algebra and go from maybe here to here and there to there. So what I want to notice, though, is in this expression, whenever I have an omega, it's divided by an omega n. So this ratio of the forcing frequency to the natural frequency, right, it appears together. So in fact, we can identify this ratio. So it's omega divided by omega n as a new parameter, right? Kind of like the damping ratio, right? But this parameter r will be known as the frequency ratio. So again, it's the ratio of the forcing frequency to the natural frequency. And as a result, this expression becomes really kind of nice. Right? We again have this F naught over K. And what's left is 1 minus r squared, quantity squared, 2 zeta r, quantity squared. So when we're looking to understand how this system responds, again, it's important to understand, right, what are the kind of the important quantities that we need to calculate. Obviously, the damping ratio is in here. But now we see that the really important thing, it's not omega by itself or omega n by itself, but in reality, it's this ratio, it's this frequency ratio, right? What's the forcing frequency relative to the natural frequency of the system? You know, frequencies, we can think about those as related to time scales. So if the frequency is high, that means the time scale is short, right? High frequency oscillations, right? Things happen on a really short time scale. If the frequency is low, then we have a much longer time scale. And so what we see is that the forcing frequency appears in this as its value relative to that natural frequency, or kind of the intrinsic time scale of the system. Now let's do something similar for the phase. Let's factor this m out of the denominator, right? So we have m, this becomes k over m minus omega squared, and the numerator will just stay the same. But once again, we can write this in terms of the natural frequency and damping ratio. So b omega over m, well, that was 2 zeta omega n times omega, and k over m is omega n squared. So we can write the tangent of the phase in this way. Again, damping ratio, natural frequency, forcing frequency. Or we can do something similar to this last step. We can factor out a k from the denominator, right? So k, we end up with 1 minus m omega squared over k. And again, b omega over the top. But here, this reduces to 2 zeta r, and 1 minus r squared. So in terms of this frequency ratio and damping ratio, the amplitude can be written as this. And again, remember it's scaled by this f naught over k. And the phase can be written like this, 2 zeta r divided by 1 minus r squared. So we really kind of simplified our expression for the amplitude and phase in terms of these two fundamental parameters. Zeta, the damping ratio, which has kind of always been there, and now the frequency ratio, which is new to our analysis of this harmonically forced system. So let's see how these behave as we change zeta and omega n. All right, so here it is again, right? This is the amplitude, and this is the frequency ratio, and we'll first focus on this amplitude calculation. And I'm going to write this in a specific way. The amplitude I'll write as, again, f naught over k. And this other stuff I'm going to identify as m. And it's a function of r and zeta. And here, this m is precisely 1 divided by this square root. Right, so m of r and zeta is defined as 1 divided by 1 minus r squared, 2 zeta r, quantity squared. This I refer to as the magnification factor. That's what we call it. So why do we call it that? Well, because if I look at this relationship, we can write m in the following way. M of r and zeta, right? Basically just divide f naught over k by x. How do we interpret this? That's really what we're after here. Well, the numerator, we can think about that as the dynamic amplitude, right? So if I drive this system with frequency omega, forcing amplitude f naught, then x is the amplitude of the response, right? So again, we'll say that's the dynamic amplitude. Or the amplitude of the response to dynamic forcing. Well, what about the denominator? Let's go back and think about our system. Go back and look at this. What if I applied a force of value f naught, just a static force, a constant force of f naught to this block? Well, in that case, we could solve the statics problem and find the displacement of the block itself. It would just be f naught over k. Well, that's what I have here. So really, we can interpret this quantity as the static displacement to a force of identical amplitude, right? But a static force in this case. So we'll call this the static amplitude. And so the magnification factor is the amplitude resulting from the dynamic force, again, a time-dependent force with amplitude f naught, divided by the amplitude resulting from a static force, just a constant load, but again, value f naught. And this magnification factor represents the magnification of the dynamic response compared to the static response. Again, that's kind of why it gets defined as the magnification factor. But this is a really nice physical interpretation for this quantity. So now let's go and see, how does this thing behave? Well, let's look at a couple of test cases. And here I've sketched them out in light gray so that I can trace them over accurately, basically. Let's look at a couple of simplifications first. The first one we'll look at is zero damping. Right? So if the damping ratio is equal to 0, then the magnification factor is just 1 divided by the absolute value of 1 minus r squared. the square root of a square, we'll take the positive branch of that square root always. So this is just the absolute value. So let's do that in red. So if I plot this function, and here we're plotting the magnification factor as a function of r, and r equals 1, again, that's actually when the dynamic and static amplitudes are the same, is where things start off. And essentially, we get a picture that looks like this. That's going to be in red. Again, zeta is equal to 0. Now, notice that as r approaches 0, for any value of the damping ratio, then this term approaches 1. So regardless of the value of the damping ratio, all of these curves, and we're going to draw these for various values of the damping ratio, end up approaching 1. So what happens if we take a bunch of different values of zeta? Well, it ends up looking like this. Right? So if I take, for example, zeta small, we have a picture that looks like this. Right? So this is actually the curve for zeta is equal to 0.1. Let's make it a little larger. Right? Say zeta equals 0.2. We end up with this curve. Right, so here's zeta is equal to 0.2. What happens if I make it a little larger? Let's do that one in light blue. We end up with a curve like this. This happens to be zeta is equal to 0.5. A little bit larger, right? So let's take zeta is equal to 1. We end up with a curve here. Finally, if we make zeta fairly large, zeta is equal to 4, we end up with a curve that follows this line. So again, as we vary zeta, the damping ratio, right, these curves begin to drop. So really we can say, kind of increasing damping ratio. So the more damping we add, the lower these curves are. At r equals 1, then the amplitude ends up reducing to 1 divided by 2 zeta. We actually define this as the quality factor, or Q. So if we can measure the amplitude at r equals 1, where the system is forced at its natural frequency, right, then again, that's only dependent on the damping ratio. And again, for historical reasons, that's defined as the quality factor. So if we gave you the quality factor of a system, you could immediately determine the damping ratio. The other interesting thing that happens at r equals 1 is if the damping is equal to 0 at r equals 1, what happens? Well, this term is vanished, and looking at the magnification factor, it becomes unbounded. Right? So in that case, the amplitude of the response is unbounded. We'll talk a little bit about that later, but we'll say that the system is in resonance. So for a small forcing amplitude, right, we can get a very large amplitude response when you're driven with low damping near resonance. So again, going back and interpreting these results, if m is greater than 1, then the response of your dynamic system is actually larger than the response of the corresponding static system. So that dynamic loading actually amplifies the maximum response of the system. While if m is less than 1, right, so that would be down in here, then the dynamic response is smaller, actually, than the static response. And so what we see is that increasing the damping, right, tends to reduce the magnification factor and tends to reduce the amplitude of the response. Let's go and look a little more into this magnification factor. So again, we're looking for cases and instances where the system response is larger with the dynamic forcing. So in particular, let's look at the maximum amplitude. So for example, for a value of damping of zeta is equal to 0.1, the maximum response occurs here. For a value of zeta equal to 0.2, then the maximum response is lower, right? It actually shifts to the left. If we increase the damping ratio to 0.5, this maximum response again moves to the left and drops. There actually comes a point where we get no maximum response in the interior. Instead, the maximum response occurs over here on the boundary. So when does this happen? Well, we'll say that the maximum amplitude and we'll denote this as the m magnification factor is equal to this specific value m star, occurs at a specific frequency, right? So we'll say that specific frequency is r star, and it depends on the zeta, right? So for zeta is equal to 0.1, right, we might get m star r star, right, that corresponds to this point. If zeta is equal to 0.2, well, let's color that green. So we might have m star r star, right, that corresponds to this value. So each one of these values depends on the damping ratio. Well, how do we find these? A little bit of calculus. Here, the slope of this curve as r changes is equal to 0. So really, we'll just go and evaluate the slope of m as a function of r, and we'll set that equal to 0. Well, okay, so we can calculate this. Here, I'll just tell you what it is. It's minus 2 times 1 minus r squared times minus 2r. Really, all I'm doing is taking the derivative of this function with respect to r. And so I did this ahead of time. Please pause the video right now and work out this derivative. You'll end up on the denominator with 2 times 1 minus r squared plus 2 zeta r quantity squared. All of that to the 3/2 power. So again, this is the derivative. And this maximum occurs when this derivative is equal to 0. Okay, well, the nice thing is that this vanishes when the numerator vanishes. And the numerator is much easier to deal with than the whole thing. In particular, we can simplify what we have here into the following form. Right? So again, if r is equal to r star, then we want 4 times r, 2 zeta squared minus 1 plus r star squared equals 0. So again, just take this numerator and you can factor out a 4r from each one of these terms. And then what's left is here in parentheses. So we actually have two solutions here, right? One solution is r star is equal to 0, right? If this is 0, then 0 is equal to 0. The second solution corresponds to this piece. So solving that, we end up with 1 minus 2 zeta squared. So again, we actually have two solutions here. and then returning this back to the magnification factor, right? We see that m star, which again is m of r star and zeta, ends up, well, if r is equal to 0, m is equal to 1. And then our second solution is 1 divided by 2 zeta, 1 minus zeta squared. Notice that if zeta is too large, we don't have this second solution. So for example, zeta is equal to 0.1, I have a 0 slope at the origin, right? That's this solution. And then I have 0 slope out here. Well, if zeta is 4, the slope only vanishes at the origin. So this peak, which happens for m greater than 1, only occurs if this second solution exists. Right? So m star is greater than 1 at r equals r star only if the damping ratio is less than 1 over the square root of 2. So if zeta is sufficiently small, we actually see that the response peaks for some positive value of the forcing frequency. As I increase the forcing frequency, or equivalently r, right, because remember r was omega over omega n. So as I increase the forcing frequency, the amplitude begins to rise and reaches a maximum and then begins to drop again before becoming less than 1. However, if zeta is greater than 1 over the square root of 2, which is about 0.707, then as I increase the forcing frequency, the response simply drops. This critical level, zeta is equal to 0.707, right, gives me a response curve like this. Okay, so we see that it's essentially 0 slope at the origin and just begins to drop off. The other important question is, for what values of the forcing frequency is the magnification factor greater than 1? When is that dynamic amplitude greater than the static amplitude? Well, again, it depends on what the damping level is. Right? So if zeta is less than 1 over the square root of 2, then for r between 0 and it turns out, you can work this out. When does this cross 1 again? It happens to cross 1 at a value of the square root of 2 times the maximum value, so r star, then m is greater than 1. And for larger values of the forcing frequency, m is less than 1. So again, this implies that the dynamic amplitude is greater than the static amplitude if r is less than, well, square root of 2 times r star, right? So for the forcing frequencies that are sufficiently small, the amplitude is actually increased. But if zeta is greater than this value, then the maximum response occurs at the origin, or essentially in the static forcing case when omega corresponds to 0. Now, you think about 0 frequency as a static kind of load. So again, in this case, the maximum response occurs at r equals 0, or the static forcing amplitude is always greater than the dynamic forcing amplitude, right? So again, as I increase the frequency, that amplitude just continues to drop. So when we're talking about the dynamic response of these systems, right, it's important to know these things. For light damping, you can actually get increased amplitude with the time-dependent forcing, if that forcing frequency is low enough. And low enough here means square root of 2 times this value. But if the damping is large, then the response amplitude to this dynamic forcing always drops, right? So as we increase the forcing frequency, right, the response amplitude just continues to decrease. So looking at this picture, we really have a description of how the amplitude changes, in particular as R changes, or back in terms of the physical parameters, as the forcing frequency changes. We see that for low values of damping, as we increase the forcing frequency, the amplitude actually rises. We peak at some forcing value that's typically near the natural frequency of the system, maybe a little below, before dropping off again at higher forcing frequencies. And eventually the forcing frequency becomes so large that the amplitude of the response is really small. For larger values of damping, that amplitude just simply rolls off as we increase the forcing frequency. As R increases, this magnification factor basically drops off monotonically. Increases in the forcing frequency lead to decreases in the amplitude. But what about the phase? That's the other part. Well, let's look at that. Here again, we have our phase condition. Tangent of phi is given here. Again, R is the frequency ratio. So we'd like to be able to, given these parameters, identify phi. Well, because tangent is multi-valued, remember that tangent is positive in the first quadrant and positive in the third quadrant, negative in the second and fourth quadrant, then it leads to maybe a bit of ambiguity about what phase shift to pick. But in looking at this fraction, we can actually figure that out. So let me go and write the tangent of phi again, slightly differently. In general, 2 zeta r, we could write that as some constant times sine of phi. And the denominator would be, again, some constant times cosine of phi. Obviously, these constants would cancel out because tangent is sine over cosine. And again, that's got to be 2 zeta r and 1 minus r squared on the bottom. So when it comes time to figuring out which quadrant we're in, are we in the first or the third if tangent is positive, or the fourth or the second if tangent is negative, really what we want to do is look at the sign of the numerator and the denominator. So here, n times sine is equal to 2 zeta r, and n times cosine is equal to 1 minus r squared. I'm not really making a big deal about what this constant is. What's important here is are these quantities positive or negative? Well, assuming that damping is positive, natural frequency is positive, frequency positive, all that kind of stuff, then clearly this quantity is greater than 0, which means that sine has to be greater than 0. Our phase shift is either in the first or the second quadrant. Those are the locations where the sign of phi is positive. Now, if it's in the first or the second quadrant depends on cosine. In the first quadrant, cosine is positive. In the second quadrant, cosine is negative. So looking at this second term, we can determine whether or not we're over in the first quadrant or the right quadrant. So in particular, let's consider an angle phi maybe here. Right? So let's call this phi 1. And for this value of phi 1, cosine of phi is positive. That implies that r has to be less than 1. Because, again, cosine is, the sine of cosine is the same as the sine of 1 minus r squared. Right? So over here, r is between 0 and 1. Notice that if r is equal to 1, then the denominator here is 0, tangent is undefined, but sine is still positive. So r equal 1 implies that phi is pi over 2. Our last case would be in the second quadrant. So maybe we're at an angle phi 2 over here. Well, now cosine is negative, so that means that r has to be greater than 1. so that the cosine of phi is negative. So again, kind of looking at these, we see that if r is equal to 0, then the phase shift is equal to 0. If r is equal to 1, then the phase is pi over 2. And we'll do everything in radians. If r is between 0 and 1, then the phase is between 0 and pi over 2, right? So we're in the first quadrant. Finally, if r is greater than 1, then the phase is between pi over 2 and pi radians. So again, this phase shift is always between 0 and pi. I will remind you that when we looked at our solution back here, this phase was actually a phase lag, right? So positive values of phi indicate that the response lags the forcing. So we can plot these as r varies for different values of zeta, just like we did before. And so we'll start off if zeta is 0. Notice that the numerator is 0. So that means that the phase is either 0 or, for r equal 1, pi over 2, or if r is greater than 1, pi. So we have a discontinuity in the response. Right, we'll kind of indicate that with a dashed line. And open circles here and here. So again, if zeta is equal to 0, the phase is 0 if r is less than 1, and pi if r is greater than 1. And then exactly at this value, it jumps to pi over 2. As we increase the damping, it kind of smooths this curve out. Right? So positive damping, but small, gives us a plot like this. And again, continuing to increase the damping gives us the following. Let's just keep drawing these curves. And we'll notice something interesting in just a second. Here, these values correspond to the values that we chose for the magnification factor. And so zeta equals 1 is given here. Finally, if zeta is large, say zeta is equal to 4, we get a value that looks like that. So once again, we see that increasing damping, or in this case, increasing zeta, kind of tends to smooth these curves out. Once again, phi must lie in either quadrant 1 between 0 and pi over 2, or quadrant 2 between pi over 2 and pi. I will caution you that when you are evaluating things on your calculator, calculators typically give you values in quadrant 4 or 1. So if the tangent is negative, you may have to make that transformation into quadrant 2 based on what your calculator says. So one interesting thing here is that all of these curves pass through r equal 1, phi equals pi over 2. So independent of the damping ratio, if r is equal to 1, the phase shift is pi over 2. So when forced at resonance, and remember that resonance implies that omega is equal to omega n, or r is equal to 1, then the phase shift is equal to pi over 2, and this is independent of the damping ratio, zeta. So we can actually use this fact to perform system identifications. Given a response, can we identify what parameters gave rise to the response itself? If you can identify the forcing frequency for which the phase is pi over 2, then you immediately know the natural frequency. Again, measuring the amplitude and phase, and in particular measuring x and phi for, harmonic forcing, amplitude f naught, frequency omega. If we can identify this resonant forcing and the static displacement to a constant load of magnitude f naught, then we can determine the parameters of the system. How does that work? Well, if we can identify the natural frequency, and let's say that this forcing frequency is omega star, then k over m, which is the natural frequency squared, is omega star squared. So again, the idea is that I have identified a specific frequency omega at which the phase shift is pi over 2. Then that gives me a relationship between k and m, because that's got to be the natural frequency. Then if I can measure the static displacement, say delta, well, that's just f naught divided by k. I can use these two to determine actually k and m. All right, so here k is obviously f naught over delta. Then solving for m is equal to k divided by omega star squared. Again, that forcing frequency that we identified. Or finally, f naught divided by delta omega squared. So making these two measurements, we can identify the stiffness and the mass. Well, what about the damping? That comes back to the quality factor that we identified earlier. At resonance, recall that the amplitude is f naught divided by k times the quality factor, or f naught divided by k times 1 divided by twice the damping ratio, because this was the quality factor. I mean, this is how we defined the quality factor, or this is the amplitude when forced at resonance. So now, and I won't show you all the algebra, but there's a little bit of algebra. Just write the damping ratio in terms of the system parameters and solve for b. When I do that, I get b divided by f naught times the amplitude at that value. Right? Let's actually call this x star, right, to be in line with the omega star, times omega star. This forced system actually provides a really useful way of identifying parameters. And this system identification process is relatively common. If you have an unknown system, right, and you'd like to figure out what single degree of freedom model best fits that unknown system, then all we have to do is take some measurements, drive the system until we find the resonance, or we find the phase shift to be pi over 2, and then we can go through and we can identify equivalent stiffness, mass, and damping for the system. So this idea of resonance is really useful. Well, I do want to go and talk a little bit more about what happens in resonance, and specifically what happens when there's no damping. Remember, we said that if there is no damping, then x of t is x times sine omega t minus phi, where the amplitude is 1 divided by the absolute value of 1 minus r squared. And the phase shift in this case is 0 divided by 1 minus r squared. So it's either 0, pi over 2 if r is equal to 1, or pi if r is greater than 1. Now, actually, I can combine these two, right? If r is not equal to 1, then x of t is f naught over k times 1 over 1 minus r squared times sine omega t. I basically pulled this phase shift out into the amplitude, and the numerator becomes signed again. Or actually, written back in terms of the physical parameters, k minus m omega squared times sine omega t. But what happens if we're driving at resonance? So if omega is equal to omega n, which again, square root of k over m, then this solution no longer holds because the amplitude is undefined. Instead, we have to return to the differential equation and solve that. And what we find, actually, is that the particular solution looks like minus f naught, the forcing amplitude, divided by twice the frequency, now times t cosine omega t. So, in fact, this term in parentheses kind of looks like the amplitude, except now the amplitude is not constant. It actually grows linearly in time. So, as time goes by, this response gets larger and larger. Right, so here, if we were to go and plot this, right, initially we get a really small amplitude, and as time gets large, this amplitude begins to grow. Right? And I've kind of sketched this lightly, and I'm trying to trace over it to emphasize the growth in the amplitude. Right? So this curve just increases linearly in time, and as promised, the amplitude grows unbounded. So the last thing I'd like to discuss today is what happens when we vary other parameters. You know, this idea of magnification factor and the phase shift that we have developed is really useful when we talk about variations in the frequency. Right? As we saw here, this frequency ratio is omega over omega n. Right? So changing the forcing frequency is just like changing r here. But what happens instead if I change, say, the stiffness, right? Or if I change the mass, or maybe even the damping? Well, so we can look at what happens with other parameter variations. I'd like to start off and notice what happens if we keep the natural frequency and damping ratio constant, but allow the physical parameters to change. Right? So here we can write any two of these in terms of a third. So for example, the stiffness is the mass times the natural frequency squared, and the damping is the mass times 2 zeta omega n. We've seen before that really the important things are the damping ratio and natural frequency. So if we keep the damping ratio and natural frequency fixed, then we basically are back to our magnification factor and our phase diagram. And it independent of the actual values of k and m and b. So for fixed damping ratio and natural frequency, scaling the system, it leaves the magnification factor and the phase shift unchanged. Now, it would alter the amplitude, right? Because after all, the amplitude is f naught divided by K times the magnification factor. But this piece would stay the same, right? The only thing that would change is the amplitude would get scaled up and down as M or B or K effectively were scaled. However, if now we just change one of these parameters, right, what happens? Well, we actually kind of did this before, but I can write the amplitude in the following. I'll factor out a value of K, and we end up with 1 minus m omega squared over K squared plus b omega over K. So now, in this case, what happens if I just change m? So that's shown here in this first set of plots. Notice that everything here is constant except for m, assuming, again, that k and b and omega and f naught are all held fixed. So varying the mass ends up changing the amplitude in the following way. Here, these curves are all shown for increasing b. And likewise down here in the phase, this is what happens when we increase the damping. It looks very similar to what we had before, although notice on the left, as the frequency decreases, the amplitude at lower and lower frequencies drops as well, right? It no longer goes to a constant value. And the same with this phase, right? The phase for low frequencies begins to shift, right? And this has to do with the fact that omega here is actually some finite value. It's just a fixed value. Looking at this phase plot, we see that if m is small, then the phase is 0, right? So we're in a condition where r is less than 1, back in our magnitude and phase plots originally. While if m is large, right, that moves to a case where r is greater than 1. Right? Again, the phase goes to pi. When varying the stiffness K, we can do a similar thing. So we'll take this expression and actually factor out the m omega squared now. Right? So we end up with f naught, m omega squared, and then what's left is, well, here, k over m omega squared minus 1 quantity squared plus b over m omega squared, and all that's over 1. Once again, let's look and see what happens when we vary the stiffness K. Well, we get a similar picture. Right? So this is now varying K alone. Remember, m is held fixed, omega is held fixed, and once again, these different curves are drawn varying or increasing the damping, B. The amplitude actually looks very similar. Once again, if the stiffness is small, then the amplitude is finite, but it does change as the damping varies. We see our resonant peak at m omega squared. So once again, k minus m omega squared is equal to 0. And then that drops off as the stiffness continues to increase. The big difference between varying the mass and varying the stiffness comes in terms of the phase. For small values of the stiffness, we see that the phase is actually pi. So that would correspond to r greater than 1 back in our magnification factor phase plots. While if k is large, now we're back into a situation where r is less than 1. So these phase curves for varying mass and stiffness are kind of opposite of one another. Low values of stiffness indicate high values of r. Low values of mass indicate low values of r. And again, that makes sense because, of course, r was omega divided by omega n, which is square root of m times omega divided by square root of k. Right? So if m is small, r is small. If k is small, r is large. So we've looked at how the system responds to various changes in this lecture. Originally, we focused really on variations in R and identified this magnification factor. Physically, these can be identified directly with changes in the frequency. And later, we saw how changing the mass alone or changing the stiffness alone changes the response of the structure. Right, so that's it for today's lecture. It's just a description of really understanding how the response varies as we make parametric changes to our system. So that's it. Thanks again. If you have any questions at all, please let me know. Always looking for comments and feedback. Thanks. Take care. Bye.